Let's look at a chaotic, nonlinear dataset. Classic linear regression models fail here. They cannot map this dense, clustered topology without extensive manual feature engineering. The algorithm that solves this is the decision tree. It operates as a discriminative, non-parametric machine learning model, far more complex than a basic yes or no flowchart. Formally, a decision tree induces a piecewise constant function. It mathematically partitions the feature space into distinct, non-overlapping geometric bounds. In this equation, Rm represents those individual disjoint regions. The algorithm has sliced the total feature space into axis-aligned hyperrectangles. For any data point that lands inside one of those bounds, the model assigns Cm, a constant prediction value, which is simply the mean response or the majority class of the training data within that specific rectangle. This structure requires zero distributional assumptions. Handles continuous and categorical data natively, without feature scaling, and it detects nonlinear interactions automatically. To master modern tabular machine learning, we have to look inside this model. We need to derive its splitting criteria, expose its fatal variance flaw, and see how mathematical regularization saves it from itself. We will see that the same recursive process that allows the tree to fit complex data also provides the exact mechanism for its eventual instability. The engine behind this geometry is the CART algorithm. Its singular task is to find the mathematically optimal split in a multidimensional feature space. At every node, the algorithm scans every feature, designated as J, and sorts the unique values. For each feature, it evaluates candidate thresholds, labeled S. It calculates an impurity score at every tick, searching for the maximum decrease. When it locks on to the lowest score, it executes the split, dividing the space into two child regions, R1 and R2. This binary splitting process is then applied recursively. The algorithm moves into each new child node and runs the entire exact search again. This is a greedy search. Each cut is locally optimal, designed only to minimize the impurity of the immediate data subset sitting in front of it. Because it optimizes locally, it ignores the future. A perfect split right now might force a globally suboptimal tree structure several levels deeper. CART cannot plan ahead. It constructs its entire geometric universe, one strict axis-aligned slice at a time. To know if a slice actually improves the model, the algorithm requires a formal mathematical measure of impurity. This is the Gini impurity equation used by CART. It measures the probability of incorrectly classifying a randomly chosen element in a specific node. If a node holds 40% class A and 60% class B, we square those proportions, sum them, and subtract from 1. The Gini impurity evaluates to 0.48. For a binary classification problem, this metric peaks at a maximum bound of 0.5. That happens when a node is perfectly mixed, completely split 50-50. The alternative measure is entropy, used by the C4.5 algorithm. Running the exact same 40-60 node through the entropy equation yields a score of 0.97. Data scientists often debate which metric to use, but these two functions almost always produce identical tree structures in practice. The scikit-learn library defaults to Gini for a purely pragmatic reason. It skips the computationally expensive logarithm operation required by entropy, allowing the model to train faster. When recursive partitioning runs without stopping criteria, the math begins to fail. If we look at this depth versus performance chart, we see that a fully grown tree will continue splitting until it isolates every single data point. The training error drops to an absolute 0. But the validation error tells the real story. Once the depth passes a critical threshold, the model starts memorizing noise instead of signal. The tree has developed extreme variance. This creates structural instability. Shifting a single training point near a decision boundary can completely rewire the entire downstream architecture of the tree. The second major trap occurs in regression trees. Watch what happens to the prediction line when the input moves past the bounds of the training data. The prediction goes flat. A leaf node can only output the mean of the training observations it holds. The tree is entirely blind to any linear trends outside the range of its training boundaries. The third trap affects feature importance, specifically mean decrease in purity, or MDI. The algorithm's exhaustive search evaluates every unique value as a potential cut. This means high cardinality features, like unique identification numbers, receive artificially inflated importance scores, simply because they offer the algorithm more chances to find a split. To extract unbiased feature importance, you must rely on permutation importance, or shop values, instead of the default MDI. Without regularization, the tree simply encodes the noise of its specific sample, failing as soon as the distribution shifts. Basic heuristics, like capping the maximum depth, aren't enough to force true generalization. We need mathematical regularization. We apply cost complexity pruning, a post-training method that actively penalizes the size of the tree. In this equation, C of t is the total misclassification cost. We add that to the total number of terminal leaves, represented by the absolute value of t. The alpha parameter is the complexity penalty. As we scale alpha up, the penalty for complexity increases. The algorithm identifies the terminal subtrees that contribute the least to overall accuracy and collapses them into single leaves. We find the optimal value for alpha by iteratively testing these pruned tree sequences against a holdout cross-validation dataset. By forcing this trade-off, we intentionally increase the model's bias by a small margin. In exchange, we achieve a massive reduction in variance. Pruning saves the tree from its own overfitting perfectionism. It forces the algorithm to mathematically justify the price of its own complexity. Even an optimally pruned tree has a hard ceiling on its stability. To push past this, we shift from optimizing a single logic path to averaging across an entire forest. In the expected mean squared error decomposition, a single deep tree provides excellent low bias, but suffers from catastrophic variance. Look at this equation for the variance of an averaged ensemble model. Bootstrap aggregating, or bagging, trains multiple deep trees on different data samples. By increasing b in the denominator, the total number of trees, we drive the entire right side of the equation toward 0. But we hit a roadblock at the row term. If all the trees analyze the exact same features, their predictions remain highly correlated. Row stays high, and the variance stops dropping. The random forest algorithm introduces a vital innovation. At each split, it restricts the trees, forcing them to choose from only a random subset of the available features. This random feature subsampling snaps the correlation between the trees. The row term collapses, and the total variance of the ensemble plummets. Combining the low bias of deep trees with a variance-destroying aggregation technique produces the state-of-the-art power of tabular machine learning. The single decision tree is a brilliant mechanism for isolating logic into readable rules. But fully understanding its geometric boundaries is the only way to harness the forests that rule modern data science.